All right, so in the last video, I thoroughly went through the concept of different components of convolutional neural network, and we have seen like what are the inner workings of a convolutional operation, then the max pooling, then how also the concept of stride, and also the concept of like the fully connected layer, which we use at the end of the convolutional neural network. Now let's put everything together and build a full functional convolutional neural network on a Cipher 10 data set, right? So this Cipher 10 data set has 10 classes. So these are the classes which are the label classes for each of the images. So each image will belong to either of this 10 class. So it's a multi-class classification where the number of classes are 10, right? So these are like few data pre-processing stuff where we are kind of downloading the trend data set and also test data set. Then we are also creating transform.compose, which can act as a transforming the images. And this transform can be very specific to your train data set and also test data set, right? So the in if you remember, like when we were talking about the regularization concept, right? When we have like underfitting problem, or we have like generally we have overfitting problem, right? So in that case, we want to generalize our model. To generalize our model, we need a lot of more examples, training examples, and that training examples will can which can help the model to generalize while learning the network, right? So to generalize the model and to get more training examples, what we can do is we can do augmentation of the images, right? So in some of the cases, you can do a random flip on the image, you can do a random rotation, or you can center crop the image. So all this thing you can do on your training data set, right? And also you can have a mean and standard deviation, and all these things you can incorporate while composing this transform, right? So you can do this transform.compose, and then you can specify what are the image augmentation you want to do, right? So here we are kind of doing a random resize crop. Also we can do a horizontal flip, random rotation, center crop. The color jitter you can also introduce for doing the image augmentation. Then you need to convert that image to a tensor, and in the end you need to normalize the image with a set of mean and standard deviation, right? So I have given this examples that for you to like pick up uh, the particular augmentation you want to use for your use case. So just be careful that in some of the images you don't want to use all the image augmentation, right? So for an example, like if you are classifying handwritten digit, and if you are doing a full flip, then your 6 will become 9 and 9 will become 6, right? So that will be a wrong signal to the model, so you need to be careful while doing this image augmentation, and that will be very specific to your use case and the data set on which you are working on, right? It is also advisable that you create a two compose or two transformation separate for training and test set. So this is the example which I have shown here also. Like I'm doing more image augmentation in case of training data set, because while training the model, I want to introduce more examples which will be fed to the model, and the model will be kind of generalized while doing the learning, right? So that we don't need to do in case of test data set, right? So I have also provided the documentation link where you can find out the details of this image augmentation techniques, and that you can try it out according to your use case. Right. So once we create the data loader, the train loader and test loader, then it's what we are doing is we are just picking up one batch of train loader, and we are checking what would be the size of my image and the level, right? So the sizes of image is 10 comma 3. So there are three channels. This all these images are color images, so we have three channels, then the height and width, right? And we, as the batch size is 10, so there would be 10 labels corresponding to each batch of images, right? Then we kind of define the architecture of my convolutional neural network, which will be a combination of a convolutional operation, then a max pull, then again a convolution operation and max pull, and in the end we will integrate a fully connected layer where the last layer will have uh, 10 nodes because we are doing a multi-class classification and uh, we have 10 labels for each image, right? And where one of the node with highest probability we will select as an output, right? So now you might wonder, we have 3 dimensions in our image, right? But why we are uh, considering here the conv 2D, right? Why not conv 3D? So this channel which we have in our for color images, that generally we don't consider as a dimension. That is a channel uh, for indicating if the image is a color image or a grayscale image. So that's why we kind of use this conv 2D where it generally the dimensions are height and width. So the channel we are not considering as a dimension. That's why in PyTorch convention, this we call it as conv 2D. Now the syntax of this operation is like you mention the input channels, then you mention the output channels, and then you mention the kernel size. So kernel size is nothing but the number of filters you want to use at that particular convolutional operation, right? And that will decide how many channels which we will have after doing this convolution operation, right? Then we have this stride equals to 1, which is these are like by default values, the default values. Then we have the padding equals to 0. And also the by default, the bias is equals to true, right? So this is like the first convolutional layer, and then we have the second convolutional layer, and in the end we have a third convolutional layer, right? And also we have pooling layers, which will do a max pooling on this, which is like a 2x2 filter, which we will run through on the image, and that will kind of reduce this height and width of the image. And after that, what we will have is we will have fully connected layer 1, fully connected layer 2, and that is the last fully connected layer, where at the output layer we have 10 nodes, right? And we also introduce dropout to reduce uh, the variance in the model output, right? Now, this is the forward function, which is very similar to what we have been discussing in this series. So we at first pass the image through a convolutional operation. Then we introduce the nonlinearity by ReLU. Then we introduce the pooling layer, right? So similarly, we do it for the other convolutional layers, like the convolutional 2 and convolutional layer 3. And once we have that, then we kind of flatten the image and we introduce a dropout, and we pass that input to the fully connected layer 1, and then we again add a dropout, and in the end we have a fully connected layer 2, right? And this is the architecture of this. Now, I have mentioned specifically for your understanding what would be the output shape of after every operation, right? Now, if I just wanted to explain one of the layers so you can understand how the math is kind of working and how the dimension calculations are working for each of this layer. And similarly, you can try it out for other layers, right? So if you remember the formula is n plus 2p minus f divided by s plus 1. And similarly, we have the same component for height and width. And then nc dash. Nc dash is the number of output channels of that particular layer. And that will be driven by the number of filters that we are using on that particular layer. So if I just uh, take the example of conv 1. Here we have like 3 comma 16 comma 3 and padding equals to 1, right? So your filter shape is 3 cross 3, and nc is equals to 3, which is a channel of our uh, one filter, right? And here you see we have a value of 16, which is nothing but the kernel size. That means that we are using 16 number of filters on convolutional layer 1, right? So So I hope you got an idea, like we are using a 3 cross 3 where the number of channels is also equals to the same as the input image number of channel, which is 3 again. So 3 cross 3 cross 3, and there are 16 filters which we are using. So the output will be calculated in this way, like 32 plus 2 cross 1. So this 2 cross 1 means that padding is we are using equals to 1. So that's why this is 1. Then minus f is nothing but 3. So the value would be like 32 plus 2 cross 1 minus 3 divided by 1, then plus 1, right? And in the end, we'll be having 16 as the number of filters. So that will be the shape of the number of channels in the output image of this con1, right? So the output shape would be 32 cross 16, right? So similarly, we can do this operation for max pooling layer. So in max pooling, it will reduce the size by half. So your 32 cross 32 cross 16 image will become 16 cross 16 cross 16, right? So that is the output after doing the first convolutional operation. So I haven't shown you the calculation for second convolution operation, but that I will ask you to do as an homework for this video, and you can see if the output is matching with this 8 cross 8 cross 32, right? So yeah, that you can try it out using a pen and paper, and that will clarify your doubts how the inner dimensions are working while doing the convolutional operation. Then we kind of define the learning rate, the loss. Here we are using cross entropy loss. So if you remember, cross entropy loss always includes the softmax. So that's why we haven't used the softmax at the output layer. So after that, we use Adam as an optimizer, and then we start the training process, right? Which is very similar to what we have been discussing in this whole series. So you can see there is a gradual decrease of loss, which is a good sign for us. Like after 10 epochs, like we started with a loss of 1.04, and in the end, we ended up with 0.269. And we can evaluate once the model is trained, then you can evaluate on the test data set, and you can see the accuracy on the test data set is 72.84, right? So we are getting around 73% accuracy on the test data set. So yeah, so that is the thing which I wanted to cover in this video, like how you can using a convolutional neural network, you can build a fully functional CNN network from scratch, and without using any pre-trained model, how you can do a image classification on a multi-class data set, right? Now, you at this point, you might be having a confusion like how we will decide the shape of this convolutional filters, what would be the number of filters that we have to use. So all these doubts, just you hold on for another video. So in the next video I will talk about how we can decide all this. Actually, we don't need to decide, we use a few of the already defined architectures, and there we can use the concept of transfer learning to build proper CNN network, right? So yeah, that's all I have for this video. I hope you like this content. And if you haven't subscribed this channel, please subscribe and share with your friends. Thank you. Thanks for your time. See you in the next video.